Alright guys, so today we're going to be looking at thin film interference, alright? So, I got a couple of pictures. Let me show you these first and we'll jump right into it, alright? So, my first question today is, I've got three pictures here, one of some very fancy and pretty bubbles. You've seen this before, maybe as a kid, maybe yesterday, who knows? Fancy colorful bubbles. A DVD or a CD with shiny colors. And possibly oil that's been spilled on the ground or leaked on the ground and kind of spread out, and you see again some fancy colors. What do these things all have in common? I'll give you a minute to think. Well, not a minute. I'll give you 20 seconds to think about it, then we go on. Alright, so hopefully, obviously, other than the pretty colors, hopefully what you thought of was that these things all have a thin film. I gave you a little bit of a hint at the beginning by giving you the title of our lesson today. But a bubble is a very thin film of soap and water that's been mixed together and creating the bubble surface itself, right? The oil has, oil and water don't mix, and so the oil on the ground will spread out, so it's very, very thin on the surface of the ground. Lastly, the DVD, even the DVD has a thin film covering the surface of this where it's the data is being recorded. There's a thin film on top of that to protect it and help keep it safe. So each one of these has a thin film, and the thin film is the connection. That's the thing that's causing these colors to take place. All right. Now, before we get too deep into it conceptually, I would like for you to watch this fun video. Now, as you're watching, I'll make some comments and some notes, but I want you to be thinking about what are the things that you see, and hopefully you'll be able to learn some things from that. So the dude just took some bubble water, and he's got a big bubble thing here, and he's clamped it up so that it's vertical, right? Now, I'll give you 30 seconds to look at it and think about what you're seeing before I start talking about it. What do you see? What do you see? Well, hopefully you're seeing all the pretty rainbow colors, right? Now, what do you see as time progresses, right? Hopefully what you're seeing is that gravity, I believe this is in slow motion, hopefully you see that gravity is pulling, maybe it's not, I don't see, gravity is pulling down the soapy stuff that's in the middle. It's not gone here. Okay, it's still there, but at this point, because gravity has pulled so much of the liquid down, it's so thin up here that we're not getting the same thing happening as what's happening down here. Okay? Now, if we consider what's happening down here, what do you see? You see the rotation of the colors of the rainbow, right? Red, orange, yellow, blue. Sometimes you see the green down here, you see the green, but up here maybe not, maybe the colors, the thickness is changing too fast. That's really what I want you to be thinking about here is as gravity pulls the liquid down and it's getting thinner up here, that means it must be getting thicker down here, right? We're not getting any dripping there, so it's getting thicker down here, and as it gets thicker, it's changing the way that the colors look. That's why the bands of colors are changing, because the thickness of the film continues to change. We're going to look at why that happens on the next slide. But what I want you to be recognizing here is that we are getting those colors, right? And you can see how the colors at the bottom, the bands are getting more and more dense as the thickness increases, right? But we do definitely see all of those different colors here. There's your green and your blue and indigo and violet and all those things, and it starts over again, right? So there's got to be something to do with the thickness, and that's what we're going to talk about right here. Now recognizing that the color being shined onto this, or shown, I don't know how to speak English, the light that's being put onto the thin film is white light. And so the reason we're seeing the colors is because of the refraction of the colors. Remember, we talked about how refraction of different wavelengths is different speeds. They'll have different speeds in the medium that they're refracting in. And so because they're having different wavelengths have different speeds, then it means that the different wavelengths, you can see that the film's still up here. I think that's what they're trying to show here. But now it's so thin that we don't get the refraction anymore. But anyway, we were talking about the idea that, actually I don't remember what I was talking about anymore. So I think we're just about good. This video I think served its purpose. You could see that the colors rotated through, right? So it's not just specific thickness gives a specific color, but there is kind of a cycle, right? That it goes from red, orange, yellow, green, blue, violet, and then it goes back to those colors again, the red, orange, yellow, right? It continues to go back and rotate through the colors, all right? So I hope that as we look at this the next slide, that it helps us to understand what's going on there. All right, so a couple of things going on here as we consider thin film interference. All right, so what we have is in the center here we have our thin film, right, which has a thickness of T. All right, now as we do this, we are going to consider the simplest situation. We're not going to be considering things that are too complex. We just want to get the basic idea. All right, so if we have a wave that comes in, so the white light is coming in, or any color light is coming in at a specific angle, right? When it hits the surface, two things are going to happen. Because there's a refractive index, the light is going to bend when it gets to this new surface. In this case, the medium here has a higher index of refraction than the air, and so therefore it bends towards the normal. Okay, we also see that some of the light reflects. All right, now the light that goes through, same thing's going to happen. Some of it is going to unrefract, or it's going to refract again so that it has the same angle as the incident wave, right? Some of it will reflect off that surface and will go back up to the top. All right. Now of that, some of it will be transmitted out again with the same angle as before, while some of it will reflect and go back to the bottom. Now this process of some of the light going out and some of it being reflected is important to the thin film interference, because what this means is that now for one wave coming in, I have several different waves coming out. And the result of that is going to be that we now have the possibility for interference. Some of the wavelengths of light, depending on this distance, depending on what's being traveled here, some of the wavelengths of light will be constructive, and some of the wavelengths of light will be destructive. And that's what's then going to allow you to see the colors. Depending on which wavelengths are being constructive, those are the ones that you're going to see. Depending on the ones that are being destructive, those are the ones that are not going to appear. And so that's what we're looking at here. All right. Now, what I'd like to do next is try to talk about a little bit of exactly what's going on here. Okay. How will we know which wavelengths we're going to see and which wavelengths we're not going to see? Or more importantly, when are we getting constructive interference and when are we not? Okay. Now, one thing that we need to mention before we go on is we need to remember that, yeah, my formulas just showed up there because I touched the screen. It's okay. one thing that we want to recognize is that if we are hitting a surface with a higher index of refraction, then that means that we're going to get a phase change. Okay, and let me clarify. Remember when we did the string, you read about this in your textbook, or hopefully if we were lucky we were able to do it in class. But when this year we weren't able to do that. But when you send a pulse down a string, if the end is fixed, right? If the end is more solid than the string itself, this actually happens when you go from a string into a more dense string as well. And you send a pulse down. When you send the pulse down, when it hits this area where either it's fixed or runs into something more dense, the reflection inverts, right? So if the pulse is coming up here and it goes down, when it hits this point, some of it will transmit through, but some of it is going to reflect on the bottom side. It's going to invert, okay? If the thing that we're hitting is a free end, or if it's less dense, then we won't get the inversion. It'll still return. The pulse will still bounce back the other direction. However, it will not invert. Now this is going to be really important, because what that means is when I get to this surface between the air and the medium that has an index of refraction of n, because this n is likely larger than air, because air is n equals 1, because this index of refraction is larger, that means that when I hit this surface and only the reflection part, I'm going to have a phase change. That is not what I wanted. So phase change. It's going to invert 180 degrees, or in other words, pi. All right. Now what that means is that the light here and the light here are now out of phase, right, by 180 degrees. It's half of a wave off. So that it basically, that means if I was able to take this light right here and this light right here and put them together, they would completely cancel out because they're out of phase by pi, right? Remember when we talk about being out of phase by pi, we're talking about our curve, which is going, this is our wave, which is going up and down and up and down. If it's out of phase, then that means that one wave would be at a crest, while the other wave is at a trough, which would mean that no matter where the wave is, it's going to cancel out. Okay. Now, of course, these two cannot be put together right now because they're in different locations. But what's going to happen is this light is now going to travel down to the surface, the next surface. Now at their surface, because it's going from a thicker to a thinner, there will be no phase change. Okay? Because there's no phase change, it just reflects and it comes back to the surface. Now the question is, are A and B going to create constructive interference or destructive interference? Because the same exact thing is going to happen right here. Right? If A and B are constructive, then C will be constructive as well, because we're going to repeat the exact same process right there. If A and B are destructive, then A, B, and C will all be destructive. All right? So what we're looking at here is what is going to happen inside the thin film. That's going to make all the difference. Okay? Now, the formula packet gives these equations right here. Okay? But I'm going to take some time and go into this because these equations can actually switch dependent on whether there is a index of refraction that's higher in the medium, and then dependent on what the index of refraction below is, because that can also affect our situation. All right, so let's consider this one right here, where we go from n equals 1 to n equals something greater than 1 back to n equals 1. So we have a phase change. We talked about the phase change right here. And then there is not a phase change right here. So remember what that means is that right now, the instant after we reflect, that these two have a phase change of pi. Okay, right now they would completely destructively interfere if they could overlap. Now, of course, they're not going to overlap. They can't overlap until they actually leave the thin film. All right, So what we need to find out is, are A and B in phase with each other, or are they out of phase with each other? Okay. Now, the reality is that it depends on the thickness. And we're going to assume that it basically goes straight to the surface and straight back, because we do want A and B to be right next to each other. We've spread them out so that we can have a good idea of what this actually looks like. But in reality, these are going to be right next to each other. All right. And so basically the light will go straight down a distance of t, and then straight back up a distance of t again. All right. Now, putting this together, what is going to determine whether we get constructive or destructive interference? Well, it's the thickness. It's the thickness of the film, because that's going to be how far it travels. Now recognize, how far does this light travel? It travels t, and then it travels up, it travels t again. So the distance that it travels is 2t. Okay? Now, 2t, t is the thickness. All right? Now, the thickness we're going to see in just a minute. Okay? Now, what determines whether it's constructive or destructive? Well, if this distance right here, right? If this distance that we're looking at, the 2t, if that 2t is half of a wavelength, then I'm going to make up for the phase change that happened right here. There's a phase change of pi, and then if I go through half of a wavelength, then this one is also pi off, right? And if that's the case, because I've gone through half a wave, and if that's the case, then I'm going to get constructive interference. So that is what it's explaining right here in this first equation. Now, why is there an n? Well, because it can be an integer, right? I can bounce back and forth. I can go through that as many times as I want. So as long as the thickness, right, 2 times the thickness, d right here is representing the thickness. Okay, that's in the formula packet. Unfortunately, they use a d instead of a t, so you need to recognize that. So 2 times the thickness. And then we're going to multiply it by n. Now the n, consistent with the rest of this, is the index of refraction. That's because the light is traveling through the film, which means it's not traveling the same speed and doesn't have the same wavelength as before. Now has a new speed, new wavelength. That's going to be taken care of by throwing the index of refraction in there. All right. Now we'll look at the other side. Now what we see here is that it's half of a wavelength. But I can also go through, m also needs to be an integer. Sorry, that's the one. Integer. Positive or negative, but most likely positive, because you can't have negative wavelengths. Okay? But the integer here means that I could go through 1.5 wavelengths, right? Because if the distance here is 1.5 wavelengths, then I will still have a phase change of pi relative to the original light. If I go through 1.5 wavelengths, then by the time I get here, I'm off by pi, which means I'm matching that one right there, and I get constructive interference. All right. Now, the other scenario is, well, what if during my path here, I go through a whole wavelength? What if 2 times d, or 2 times thickness, is a whole wavelength? Okay, well, if that is a whole wavelength, then that means I'm still in phase with the original light, because whatever the original light was doing, it just goes through a whole wave and it's back to where it was. That means that this one and this one will be completely out of phase with each other, right? These two are going to have destructive interference, and that's what it's showing right down here. So what I want to show you now is, well, what happens if this index of refraction here is not air? What if it's something thicker? What if, so this is N1 and this is N2. So what if N2 is greater than N1? All right. So we still get the phase change here, right? We still get the phase change here because the transparent medium is more dense or has a higher index of refraction. But down here, because I've now changed this medium so that it has a higher index of refraction than the middle one, then now I'm also going to get a phase change of pi here. All right? So what if I only go through half a wavelength? If my thickness, 2t, is only half of a wavelength, or 1.5 or 2.5 or 3.5, okay? So I go through half a wave here and an extra half change here because of the reflection. That means that I've gone through 2 half wavelengths, which means that I no longer am off by a factor of pi. It's as if I had gone through a whole wavelength. That now means that these two will have destructive interference. Okay, this is where the formulas in the packet can be slightly deceiving, because now we just said that if my thickness is a half a wavelength, then I get destructive interference. So the thing to recognize is that when you use the formula from the packet, you have to look at the phase changes. How many phase changes will occur? If it's just like the bubble, where you're going from air to medium to the soap back to the air, then this is a correct scenario. There's only one phase change. If there's only one phase change, these formulas work fine. Okay? If I have 2 phase changes, or if I'm going the other direction and there's no phase changes because I go from high to medium to low, so there's no phase changes happening during those reflections, in both of those scenarios, we actually are going to switch these. Okay? We're going to switch the constructive interference and the destructive interference. Okay? And if we switch the constructive and the destructive, then that now means that this one will be destructive and this will be constructive. But you have to check the phase changes, because it will change depending on the scenario that you have. All right? So hopefully we'll look at that as we look at, I'm going to go through 2 examples right now, and hopefully you'll be able to see how that kind of applies. All right? So let's go ahead and do it. We'll move on to the next slide. So here's one example. I didn't show this in my original thing, but solar cells have to be coated so that light falling on it is not being reflected, right? We want as much of the light being absorbed as possible, obviously, for a solar cell. Okay, so a solar cell has a very high index of refraction, 3.5. The coating of the coating has this index of refraction. All right. So here's the scenario that we have. All right. I haven't even finished, but I really like drawing pictures so that I have an understanding of what's going on, and then I'll finish reading the question. So I've got light coming in. Here, let's change colors. We've got light coming in. The light's going to hit the surface. The index of refraction out here is 1. Okay. The index of refraction of the coating is 1.5. So then it goes into that, and of course then we get the reflection and all the other fun things going on. Okay, and then some of it's going to go into the actual solar cell, and the solar cell, it says, has an index of refraction of 3.5. Okay, so as mentioned in the first video, the last slide, first thing I want to figure out is how many phase changes are there going to be. All right, just in the going down and coming back. Okay, these are the 2 that I'm interested in. Yes, it happens over and over and over again, but those are the 2 I'm interested in. So where are my phase changes? Well, here I'm going from 1 to 1.5, right? So this reflection right here will have a phase change of pi, because it's going into a more dense material, so therefore all the waves will be inverted. Okay, now of the light going through, here I hit another surface, and note that I'm going from 1.5 to 3.5, so again I'm going to have a phase change of pi. So now what that means is when I go to my equations, rather than using the equations given where it says that the constructive interference is 2dn equals parentheses m plus 1/2 lambda for constructive, those are going to switch. Those 2 constructive destructive interference equations from our packet are going to switch because of the 2 phase changes. All right, so it says estimate the minimum thickness needed in order to minimize reflection. So to minimize reflection, I want destructive interference right here as these 2 come out. I don't want any light being reflected off. I want them to destructively interfere. All right, so the destructive interference, because I'm flipping the 2 equations, means that I'm now going to use 2dn equals m plus 1/2. These are the same formulas that I showed on the previous page and the same formulas that are in your formula packet. All right, so the question is, what is the minimum thickness? All right, so that's what I'm looking for.
So you can see here I've gone ahead and written out the formula, right? I have the wavelength. I've put in the index of refraction, which is 1.5. I put in a 0 for the M. The reason for that is because we do want the minimum thickness, and so I just want the one where the thickness gives me enough time to go through half of a wavelength. I don't want to go through more than that. That's the minimum I need to go through in order to accomplish this.
So if you plug that into your calculator, which I'm going to do on my calculator right here, and we should get our final answer, which is about 87.3 nanometers. Not sure now it goes away. There you go. Sorry, I got to figure out a better way to connect these. But that's the answer you should get. All right, so let's go on to the next example. Okay, this one will be slightly different. Okay, so this one, we've got air on the top, which has an index of refraction of 1. We've got the oil, which it gives us as an index of refraction of 1.45. And then we've got the water, which has an index of refraction of 1.33. So in this situation, how many, it's still going to, it's the same idea, right? Calculate the minimum film thickness. This time it says that when viewed at near normal incidence, a particular region of the film looks red with an average wavelength of this. So why would the film look red? Well, the film would look red because the red bouncing off is constructively interfering. And if the red bouncing off is constructive, so we want constructive interference of that red wavelength. All right. So as we look at it, we're going to, which equation are we going to use? Well, in order to determine that, we need to look at the phase changes. So when I go from 1 to 1.45, it's a higher index of refraction. So there we have a phase change of pi. Okay. When it goes through and gets to the water, the oil to the water, recognize that 1.45 to 1.33, this one is lower. And so there will be no phase change there. So I have one phase change, which means I'm going to use the same formulas that are given to me in the formula packet. All right. And so therefore we're going to use 2dn equals m plus 1/2 times lambda. And at this point we should be able to solve, because we're going to go 2 times the thickness, which is what I'm solving for. The index of refraction is the index of refraction that the light's passing through, doing its refracting, so that's the 1.45, and then equals, and again, we're going to keep it the minimum film thickness, so we're going to take out where you just want to go through 1/2 wavelength, so 1/2 times 650 nanometers. All right, we'll work that out and plug it in your calculator, and what do you get? Well, hopefully you got that D was approximately 110 nanometers. That's what I got. All right. Explain the significance of the refractive indices of oil and water with regard to observing the color. I did skip that, but we talked about it, right? We talked about the idea that the indexes of refraction are going to determine whether there are phase changes or not. Okay? And so if I wanted an extra phase change here, I would need to do something other than water here, something that's thicker, has a higher index of refraction than the oil. So what is the significance of the refractive indices? Well, they're going to determine whether there's phase changes, which then determines whether I switch the constructive-destructive interference equations or not. All right? Okay, well, that's actually it. I hope that those examples help you to understand kind of what we're looking at here, and yeah, go ahead and work some problems with it.